Everybody, this is Mina, Harrison, and Nikki coming at you from Floppy Physics, the one and only source you need to understand the teaks of physics. Today, we are going to explain the four fundamental forces of physics. Now you may be asking, what even are these? Well, you're about to find out. The standard model of particle physics states that there are four fundamental forces in our universe. These forces are gravity, weak force, electromagnetism, and strong force. The combination of these forces do everything from powering stars to keeping atoms from falling apart. They basically make up the forces of the known universe. We'll go a little into depth and explain what each type of force is, in increasing order of strength.
The first fundamental force is gravitational force. You actually experience this in your everyday life. How do you think that you stay glued to the earth? It is because the earth is exerting a gravitational force on you and attracting you to its center of mass. According to Newton's third law, however, you are also exerting an equal and opposite force on the earth. Just like how gravity keeps objects grounded, gravity is also responsible for keeping objects in orbit, such as our moon about the earth and the earth about the sun. This is because the sun has a much larger mass than the earth, which has a much larger mass than the moon. The objects with larger mass have a greater pull, allowing planetary objects to stay in orbit. You'll notice that gravitational force exists between any two objects that have mass, and the gravitational force has an inverse square relationship with the distance between the two objects. The relationship between the force responsible for causing an apple to fall to the ground and the force that kept planets in orbit, as well as how mass and distance affected these forces, was discovered by Isaac Newton. He argued through his thought experiment that the speed of an object in orbit and the gravitational pull of a planet caused the object to orbit a planet without ever hitting the ground. His laws were considered to be the most fundamental aspects of physics until quantum mechanics were discovered. This is the equation that Isaac Newton used to describe the strength of gravitational force. Since his discoveries, more has been discovered about gravitation. Gravitational force has infinite range and is carried by the graviton, a hypothetical elementary particle.
Next, there's weak force. Weak force is a force that plays an important role in radioactive decay and nuclear fusion. It is actually 10 to the 25th times stronger than gravity. The reason we don't feel this force is because it actually only has a range of about 0.1% of the diameter of a proton. Imagine how small that is. That means that weak forces only affect particles smaller than protons. Weak forces act on elementary particles called quarks, which are the particles that make up protons and neutrons. As you can see here, 2 up quarks plus 1 down quark equals a proton. Different flavors of quarks in different amounts are what determine whether a particle is a proton or a neutron, each of which is made up of 3 quarks. Weak forces alter the type of quark in a particle, thus completely changing the particle's identity. Weak forces are carried by other elementary particles called W bosons, which can be positively or negatively charged, and Z bosons, which are neutral. Weak forces are what allow nuclear fusion to happen in the sun and cause the decay of carbon-14, making carbon dating possible.
Now, on to electromagnetism. Electromagnetism is carried by the photon, and like gravity, has infinite range. It is 10 to the 36 times stronger than gravity. Electromagnetism actually has 2 different forms, magnetic force and electrostatic force. We know that these forces are one and the same because a magnetic field is generated when electrical current is passed through a coiled wire, and an electrical current can be generated using a changing magnetic field. This also happens on a much larger scale on our planet. The motion of the conductive material of the core of the Earth causes an electrical current that generates Earth's magnetic field. Earth's magnetic field is the reason compasses work. Magnetic fields always have a positive pole and a negative pole, regardless of their size. The magnetic force is always attractive between opposite poles and repulsive between the same poles. Just like magnetic force, electrostatic force is attractive between particles of opposite electrical charge and repulsive between particles with the same electrical charge. In an atom, electrostatic force attracts electrons to the protons in the nucleus. But what keeps the protons from repelling each other?
The strongest of the four fundamental forces is aptly named strong force, and it is about 100 times stronger than electromagnetic force. Like weak force, strong force operates on the subatomic level, but with a slightly larger range than weak force. Strong force is carried by the particle called gluon, and gluons glue quarks together to form particles such as protons and neutrons. This force also has a sort of residual effect called the nuclear force, and the nuclear force is responsible for keeping the nuclei of atoms together by attracting nucleons, which are neutrons and protons, to each other. The nuclear force is much stronger than the repulsive forces caused by electrostatic forces, so the protons do actually stay in the nucleus rather than flying apart due to the electromagnetic repulsion.
Another application for strong force can be seen in the energy released when a nuclear weapon detonates. The strong forces release the heat energy in a nuclear power plant in the form of steam, helping to create electrical energy. All in all, strong force effectively overcomes natural repulsions within an atom in order to keep neutrons and protons together.
To summarize, the four fundamental forces in order of increasing strength are the gravitational, weak nuclear, electromagnetic, and strong nuclear forces. The gravitational and electromagnetic forces have infinite range, while the weak and strong nuclear forces have only subatomic range. The gravitational force has been used to power robots. Passive walking robots are powered solely by the gravitational force and are able to mimic human gait when walking down inclines. The electromagnetic force has helped navigators through the invention and use of the compass. It is important to have knowledge of the effects of the strong nuclear, weak nuclear, and electromagnetic forces for understanding intermolecular forces, radioactive decay, the structure of an atom, and other aspects of chemistry. These four forces are important because they are critical to everything that takes place in our universe. Objects of mass are made up of atoms, which are held together and affected by electromagnetic, strong nuclear, and weak nuclear forces. The gravitational force keeps our planet in orbit and keeps us on the ground. Because these four forces apply to every aspect of our world, they are fundamental. Thanks for watching.